Before we start, I would recommend everyone to take a screenshot of this one. So there is a link with all the material we are going to go through. Today is a workshop, so we are going to have a couple of exercises and hands-on experience. Okay, so today we are going to talk about how you can leverage a technique which is called fuzzing to build more secure smart contract. We are going to see what is fuzzing. We are going to have exercise on how to use a fuzzer, and we are going to see a couple of best practices on how to do that. So my name is Josselin Feist. With me is Natalie Chin. We are both working at Trail of Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We have expertise in blockchain, but we also work on different spectrum of security, including cryptography or traditional AppSec. One thing that kind of differs us, I think, from other companies is that we are research-oriented, and as a result, we spend a lot of our time trying to apply program analysis in our day-to-day activities, and as a result, we have built a lot of open-source tools. You might know Slither, which is a static analyzer for smart contract, Echidna, that we're going to see today, but we have a lot of additional tools for different alt chain and so on. So today we are going to, as I mentioned, we're going to focus on a specific technique which is called fuzzing. We are going to see what it is, how you can leverage it, and we are going to have exercise for you to play a bit with it. The question, the first question that we're going to ask ourselves is how to find bugs. If I give you this piece of code, there's two functions, a function that is going to buy some token and a function that is going to compute some price to know if you are sending enough Ether. Don't need to focus too much on this. There is a bug, but we will see that later. If I give you this piece of code, how can you know if it's good or if there is a vulnerability in it? You have basically 4 techniques. The first one, unit test. I'm assuming everyone here knows what's a unit test. You should use them. They are really valuable. But in terms of security, they might not provide as much value as you can think. One of kind of evaluations that we have made internally is that we were looking at how good are unit tests in the audit that we are doing and what's the likelihood to have a bugs. And actually, there is no correlation. And the reason for that is that most of the time when you are going to write unit test, you are going to cover kind of the happy path, the things that should happen within the protocol, while usually vulnerability are going to lie in the edge case. So you should do unit tests, but they are not sufficient to prevent from vulnerability. The second technique is manual analysis. Basically, you open the contract, go line by line, trying to find vulnerabilities. This requires specific set of skills, it requires specific mindset, and usually people go through a security firm to get an audit or through bug context, as you know. There are 2 additional techniques that you can use, fully automated analysis and semi-automated analysis. By fully automated analysis, I mean tools that you can just run on your code base, they give you some result, and you have nothing else to do outside of triaging the result. One example of that is Slither. So it's a static analyzer. It's going to look for common pattern and common vulnerability in your code base. Here an example of Slither action. So it's a GitHub action that you can connect to your GitHub, and it's going to run Slither on every pull request. It's free, it's open source, and Slither has demonstrated its capability to find vulnerability over time. So I would highly recommend, if you're not using it, to integrate this in your CI pipeline. The second technique, or like the fourth one, the last, it's semi-automated analysis. What I mean by that is that you're going to use a tool, but what is it? Okay, sorry. So the last technique is semi-automated analysis. You're going to use a tool, but here you need to provide some input. You need to provide some configuration, or there is some manual intervention in comparison to Slither, where you can just run it on your code base. For semi-automated analysis, you need to provide information. In particular, we're going to use on a specific technique, which is called property-based fuzzing with Echidna.
So that brings up the question of what is property-based testing and what are we actually looking for when we're defining invariants or what we're looking for when we write property tests. At a very high level, fuzzing is very much like unit tests on steroids. It's like a cat on a keyboard or a monkey on a keyboard and like pseudo-randomly generating random inputs for your functions and seeing how your functions work and whether your functions actually work in the correct way. So fuzzing is fairly well used in traditional software. You can see that in like AFL, you can see that in libfuzz, and what they're looking for is slightly different than like what a smart contract would look for. So typically for something like AFL, it's not going to be looking for, it's going to look for program crashes. So it's going to say, oh, your code panics in this area and this is unexpected behavior. And it's basically going to tell you when your program crashes. There's no concept of crashing per se in smart contracts. So this concept doesn't really work in terms of like the EVM and like Ethereum space. What we mean by property-based testing is, from a user perspective, they're going to define invariants. They're basically going to say these are assumptions that should hold true in a code base. And the fuzzer is going to randomly generate inputs, call a function, and see whether there are violations of a certain property. So generally, we're looking for violations of a property and not necessarily crashes. So this is what we'd mean by unit testing on steroids. With unit testing, you're limited by the input range that you're specifying. So you're basically, if you set up like a unit test, the inputs that you're checking are limited by what you've defined, whereas in fuzzing, it's going to randomly generate those inputs to see whether violations are possible. So that brings up the question of what is an invariant? An invariant is basically something that should always hold true in a code base. By that, we mean something that's probably affecting system state, maybe as a end-to-end system behavior, as opposed to the behavior of like a certain function, for example. So one really good example, and one that's easy to reason about, is the concept of total supply in ERC20 tokens. With these tokens, there's a concept of like user balances and then total supply. And a system invariant that we can reason about is essentially that any user balance, regardless of whether it's the owner or another address, should never exceed total supply. If it does, then we know something is wrong within the system. We know that there's either like a bug or something wrong within the mint or some arithmetic. So this is where Echidna comes into play. Echidna is our open source smart contract fuzzer. And what that means is that we're basically going to feed Echidna invariants. And Echidna is tasked with finding what inputs are possible to essentially break a specified invariant that we're identifying. The benefit is that it's very easy to use, and we can define invariants within Solidity. So there's no context switching between different languages. We have the ability to essentially write it in the same language that our source code is in. It's also available within a GitHub action, similar to what we saw with Slither, and it works for all compilation frameworks, so you're not necessarily dependent on a single framework. So this diagram depicts a little bit more of how to think about smart contract code and invariants. So in the middle, we have the smart contract code, and this is basically just the stub of an ERC20 token. It identifies the total supply, it identifies balances, and the fact that from a transfer function that there is the opportunity for these balances to change. The property invariant we're going to get into in the first exercise, but with Echidna we're essentially going to determine whether Echidna can find a property violation of the property invariant. So pass it on to you. Sorry.
Yeah. Okay, before we go into the exercise, do you have any questions? Okay, so as I mentioned, this is a hands-on workshop, and we have a couple of exercises. You are going to find the first one at this URL, check out on the ETSCC branch, and good luck. So we are going to take 10 minutes to do this one. Nat and myself are going to walk around. If you have any question regarding the setup, or if you have any question regarding how to use Echidna, just raise your hand and we will help. Yeah, 10 minutes, so up to 50. How many of you have used a fuzzer in the past, either Foundry, Brownie, or even Echidna? Okay. How many people manage to at least run Echidna on the template? How many people manage to get Echidna running? Okay. Wave your hand if you have any issue and you need like help on the installation.
If anyone needs help with like installing Echidna, feel free to raise your hand too.
Okay, let's see the solution. So for this exercise, we have this target. We have this contract, it's a token, it has a transfer function. Most likely you can spot the bug here. There is an unchecked block and there is a subtraction. So you can have an underflow. Okay, the pointer is not working, but at this line you can have an underflow. So if you try to transfer more token than your actual balance, this is going to underflow and you're going to have like a really, really big balance. But when you look at this type of contract, you don't actually need to look for a bug when you try to think about invariant. You can just try to determine what type of invariant you want to offer this function and define it. So here the invariant that we would like to try is the one we just described during the slide, such as you have a total supply, no user should have more balance of the total supply. If you have a total supply of 1 million and a user has 2 million, something wrong is going on. So to test this with Echidna, you are just going to inherit the token with another contract. You deploy the system with an initial balance of 10,000 tokens, and you add the invariant. Here the invariant is simply a solidity function that returns a Boolean, and the Boolean is a condition. It's an invariant that we are looking for. And here the invariant is simply that the color, the balance of the color is below or equal to 10,000. Again, this is an invariant, like no one within the system should have more than 10,000, and you can describe it as a solidity function. If you run this with Echidna, Echidna is going to tell you this failed, this invariant does not hold. And to break this invariant, it's going to give you an example of sequence of transaction. Here it's only one transaction, so it's one call to some address to transfer this amount. So what is happening under the hood is that Echidna is going to take this contract, is going to call all the function of the contract. Here you only have the transfer function, but you can imagine you can have like 10 or 20 different functions with different input. It's just going to stress test the contract. After every call, it's also going to check the invariant by calling it, and if this invariant returns false, you find the bugs. And here it did call transfer, and it did transfer with 10,093. Again, you are going to trigger the underflow. The thing which is interesting here is that you define an invariance about like the kind of the behavior of the contract, but you don't need to even look at the transfer function itself to define this type of invariant. Any question? How many of you managed to find a solution for the first exercise? Oh, nice. Okay, let's go over the second one. Let's take 10 minutes-ish to go through this one. Okay, how many person managed to solve this one? Oh, nice. We're making progress. Okay, so for this one, we have this target. So we have this contract. It has some, ownership features with some access control, and it's a posable system. So you have a pause function and a resume function. And here what we want to test is that we want to test a situation where, because it's a posable system, you say, okay, I'm going to pause the system, I'm going to drop ownership so that there is no owner anymore. Can an attacker unpause the system? So can you kind of prevent, as an attacker, can you resume the execution of the contract? To do that, within our test, we are going to use a constructor to pause the system and set the owner to 0. So we lose ownership. There is no more, there is no user that can call the only owner function, or at least should not be able to. And now we're going to add a property. And here the property is simply, again, a Boolean function that returns the Boolean, and the Boolean is pause is equal to true. So you deploy the system, you pause the system, you drop ownership. Can you unpause the system? Can you kind of break this invariant? And Echina is going to say yes. And to trigger that, Echina is going to tell you that they can break the invariant by calling two functions, owner and resume. Now, if we take a closer look at the ownership contract, you will realize that there is a function called owner in the ownership contract, and basically anyone can become the owner. Like, this is a bug. This type of vulnerability is a bit old. It was more common where the constructor in Solidity was not called constructor, but it did happen more than once. The thing which is, again, interesting here is that we were not looking at the ownership contract. We were not looking at the different function. We were just looking at the posability of the system. And Echina, kind of on its own, managed to find a path to break, like our mitigation. Any question regarding this exercise? Okay, so one thing that can be kind of difficult is to find invariants. Like here in these two examples, it was kind of straightforward, small piece of code. You have like a couple of invariants that are easy to kind of define. But now, if you take like a protocol which is larger, if you are building something which is more complex, it might be difficult to come up with invariant. And having good invariant is actually the most important part of what we are doing here, because if your invariant is just 1 is always equal to 1, sure, you have an invariant, but it's not going to be valuable for the safety of your contract. And the best approach is actually really simple. Start small. Try to create an invariant that is not complex and is really straightforward. The first time you write an invariant should not break. Like the first invariant you are going to come up with your system should not lead to a bug. Otherwise, either your code base is in a really bad shape, or you were thinking too far. Don't try to write the invariant in Solidity right away. Just think about them. Think in English, like create a markdown file, text file, whatever works for you, and start by dumping idea. What should be the kind of behavior of your system, what it should be doing, what it should not be doing. And then once you have like a couple of maybe 5 or 10 ideas, go on Solidity, write them, and run the fuzzer. If an invariant breaks, either you found a bug or your invariant was false, and this is something that is actually pretty common when you start building invariant. You might have assumption on how the system is supposed to work, but actually it's a bit more complex. So it's an iterative process. Start small, start with English, then Solidity, run the fuzzer, iterate based on the result. And it's really like a process of thinking about everything that can happen in your system and or should not happen. To give you some example to be a bit more concrete. Let's say you have an arithmetic library. So if you think about arithmetic, there are a couple of invariants that usually hold for any type of arithmetics. Commutative, identity, inverse. This is like standard arithmetic operation. If you have more complex system, we saw like a couple of examples with ERC20. The balance of a user should not be above the total supply. You can also start thinking about individual function. If you have a transfer function, what should be the behavior of a transfer? Here you can think about two things. The first one, the balance of the sender should decrease, and the balance of the receiver should increase. That makes sense, right? Actually, if you write those invariants, they are going to break. And the reason for that is that there is an edge case here. If the destination is a sender, the balance is just going to stay the same. So this is an example where you can think about invariants that are straightforward, but actually the kind of expected behavior of the function is slightly more tricky. That's why this iterative approach is really important. Something to consider also is the reverting case. In the example of transfer, if you don't have enough funds, if you don't have enough money, the transfer should either revert or return false, depending on how you implement the token. There are basically two types of invariants. You are going to find function-level invariants or system-level invariants. Function invariants, as the name kind of suggests, are going to be relying on the behavior of an individual function. The arithmetic ones that we describe, commutative and this type of things, are usually function level. They can be stateless, not always, but usually they are stateless. Then you have the system level invariants, the invariants that are going to be true across any function and any call. The total balance is one of example of these system level invariants. It's usually better to start with function level invariant just to get like a better sense of where you are at and what you are trying to define. Function level invariant might take a bit more time to get them right. For the function level invariant, a simple technique is just to inherit the contract, create a function that call what you are trying to call, and use assertion. We are going to see in a couple of slides a different mode of Echidna. The first one that you used was to create a properties function, but we also support assertion within the code. The second one for system level invariant might be more complex, and one of the difficulty can be to initialize the system. If you are looking for invariants that are going to hold over 3 or 4 contracts, then you need to deploy 3 or 4 contracts, and initialization can be complex. We have an additional tool, it's called Ethino, that is going to replay your unit test. So typically, if you have a really complex initialization setup, you can use this tool just to see the Echidna so that it's a bit easier to set up. Any question? Okay. As I've kind of hinted, we have different API for Echidna. So the API are going to be the way you define the invariant. Property, Boolean property assertion, and DAP foundry. So the Boolean property are the one you already manipulated, pretty straightforward. You have a function, return a Boolean, the invariant is a Boolean. This is nice because it's easy to use. It's also easy for like system level invariant. It might be a bit easier. And you don't have side effects. You are not messing up with the code. So, you can keep something a bit more clear and clean. The assertion, so using assert, has a couple of advantages because you can add, assert in different places of the code. But it has also a couple of kind of risks. For example, if you start adding assert everywhere in your code, maybe your assertion has a bug, maybe like you add complexity. So you have to be careful where you are going to put the assertion. And the last one is the DAP or no foundry kind of API. It's kind of similar to the Boolean properties, but there is like this setup function and like the property itself. It doesn't return like a Boolean. But it's fairly similar to the Boolean properties. Okay, for the next exercise, we are going to see an example with assertion. So here you are going to, instead of using the Boolean property, you need to use an assertion to test the code. Any question? Okay, let's take 10 minutes for this one.
Like, I think at one point Solidity was shipping with like formal verification thing that was checking assertions. How is that coming along? Because I mean, at one point I think
so
it was kind of like very sneakily.
Yeah. So the question is about Solcy and the SMT checker, which is within Solcy, and they're working on it. So the SMT checker is going to work using formal verification, It's slightly different in fuzzing in the sense that it's going to use like a mathematical representation of the code to check the invariance. From our experience, the main difference, and yeah, spoiler, I have a couple of slides on this, but the main difference is that you are going to be way more efficient with fuzzing than with formal verification. From the moment you are going to try formal verification, you might need to change the code base to make it amendable for your formal method. You might need to create mocks, so like it might not be able to analyze external call, and it's just usually more complex to use. While if you check invariant with a fuzzer, from our experience, you are just going to be way faster. If you spend, let's say, 2 weeks writing on invariant, you are going to go way, deeper and broader using a fuzzer than using like a formal method-based tool. For the SMT checker itself in SolC, I think it's still a work in progress. I'm not aware of any kind of large code base using it. And for the reason I just mentioned. Yeah.
Excuse me, just to add some information. At runtime verification, we are generating the K-Foundry integration so that you will write Foundry tests. You don't need to know formal proofs. You just write Solidity and you generate proofs. So yeah, that might be.
But yeah, from kind of experience, this is going to work for simple invariant if you have like an invariant within the function. But from the moment you try to test more complex invariant, you need to add additional helper for the formal method. So this adding a support for like Foundry or Echina and everything is going to get you okay for simple invariant, but for anything more complex, it's probably not going to work as easily from our experience. Okay, how many of you managed to solve this one? Okay. So here we are more or less in the same situation where we have a token and we want to check the transfer function. However, here we are going to use assertion. So instead of having like this property as a Boolean, we are going to just have this assertion. And here the assertion are made at the end of the transfer, and you just check that the balance of like the color decrease and the other one increase. Something which is interesting here, but you have to be careful with, is that if you use assertion, you can keep the assertion in the code. If you find a way to express, like the invariant, you might be able to just keep it as an on-chain safeguard. I'm saying you have to be careful because first it's going to be more costly on gas, but which can be okay if it has additional safeguard. But writing invariant can be complex, and you might introduce a bug. So you want to be really careful to not have an invariant that is just going to break your system if you add the assertion on-chain. But it might still be like it's a kind of a trade-off that you have to consider. Okay, there are a couple of additional things to consider. For example, composability. If you look at modern systems, it's not just one contract. You might have 5 or 6 different contracts. You might interact with third party. So we have a specific mode in Echidna, which is called all contracts. It's just a flag to activate or a config file to set to true. If you set that, instead of fuzzing a specific contract, Echidna is going to call all the contracts. So if you are looking for a composability bug, this is really important. We have a couple of additional exercises. We're not going to go through them, but it's on GitHub, so I would recommend you to try them. And in particular, they are from the damn vulnerable DeFi CTF, and it's how to solve this challenge with Echidna. I'm just going to skip them. Okay, some of the questions that we receive and you might ask yourself is a comparison between Echidna and other tools. The first things to know is that nowadays there are a lot of fuzzer. You have one in dApp tool, you have one in Brony, you have one in Foundry, and probably other. It might be slightly easier to use in your first usage. For example, the one in Foundry is really straightforward to use if you are already using Foundry for testing. However, Echidna is usually more powerful. We have additional features. We have been using Echidna in our audit for more than 5 years, so it's a bit more robust, and we believe that the performance are also higher. There was a question about formal verification. From our experience, while formal verification might be appealing, it's not as efficient as fuzzing. In practice, really like the most important part of all this work is not actually using a specific tool. It's really for you to think about the invariant, really to sit down and consider them. If you do that, you have done 80% of the work. How you are going to test them, formal method, fuzzing, whatever, is only the 20, it's a remaining work. So you can try formal method, but from our experience, it's just going to be way more investment for you. There is this quote from the CEO of runtime verification. Is basically saying that you need 9 times the resource to formally verify a contract versus the one you use for development. While with a fuzzer, as you saw, it's pretty straightforward to use. As I mentioned, we have a couple of advantages, things that we did not go through during this workshop, but for example, Echidna can target high consumption as gas consumption function. So if you are looking for gas performance, you can just run Echidna in this mode. It's going to tell you which function consumes the most. And this is going to be done with fuzzing, so it's kind of more powerful than testing. We have differential fuzzing, where you have 2 implementations and you try to see if there is a divergence between both. And yeah, we have a lot of additional things. For example, we have this optimization mode where, for example, you found a rounding issue and you want to know how far the rounding can go. You can ask Echidna to try to maximize the amount of precision loss for the rounding. So these type of things are only available in Echidna as far as we know. And it's free and open source. For information, we're writing Echidna. So Echidna is in Haskell. It has been like a long discussion with the community because no one managed to contribute to Haskell. So we are rewriting it in Go. There's Medusa, it's already open source. It's experimental, it's not as mature as Echidna, but yeah, I wanted you to know about it. Okay, so as conclusion, I would really recommend you as developer or security researcher to start building this kind of process of writing invariant, thinking about invariant, and going through this iterative approach. We have a couple of additional repos. So we have securecontract.com, which contain additional exercise. We have properties which contain inbuilt invariant. For example, we have open source invariant for ERC20, ERC4626, and so on. And yeah, how many of you want to try Kine on the next project? Oh, nice. And thank you. Yeah, I'm not sure we have time for questions. No. We have time? Oh, okay, we have time for questions. Perfect. Is there any question? If you have any question, feel free to find Natalie or myself.